So good morning, everybody, to the second day of the summer school on forecast verification research. I'm Barbara Casati, and I'm going to present you verification of continuous predictance. So I'll share my screen now. Here we go. So I'll ask everybody, please make sure that you're muted. And as yesterday, you can post your questions, comments in the chat while I talk. I'm not going to see them, but Raghu will. And then some questions might be answered during the talk. If they're not, I'll take questions with the raised hands at the end of the talk, but Raghu actually can point to the discussions that were going on the chat during the talk, okay? So let me just put into presentation mode. Okay, here we go. And I think you should see the screen in full now. Okay. So I have the outline of the lecture. I'll start with exploratory methods that you have seen a little bit with Barb already yesterday, but I want to just to revisit them in light on how they are used with continuous scores. Then the core of the lecture is going to be on continuous scores. And at the end, I'm going to walk you through how to aggregate continuous statistics when you have a large volume of data. So before, as Barb said yesterday, before performing any verifications, it's always a good idea to perform initially some exploratory analysis. Graphical tools, we have many. These are two examples of graphical tools that you can use. And on the left, you have the scatter plots. These are the plots of the observations versus the forecast pair values. And scatter plots essentially is a representation of the joint distribution. On the right, you have the quantile plots. Those are the plots of the observed versus forecast quantiles. And in the reality, these are essentially the ordered values from the smallest to the largest value of the forecast. And they compare the forecast versus observations marginal distribution. So here you can see immediately there is a positive bias. Actually, no, it's a negative bias. The forecast is in the x-axis. So why do we want to perform an exploratory analysis? Well, that provides a glimpse at the overall forecast and observation characteristics and the relationship. So for example, helps identifying some peculiar behaviors, or if there is an outliers, you would see it immediately. Informs on the biases, the error magnitude, how much is the spread around the diagonal, that's the magnitude of the errors. Provides information on the linear associations or maybe other associations. Essentially helps establishing what is the most suitable verification approach to do with our data. Okay. So these are some examples of exploratory graphical tools. So at the left, you can see my mouse, so I can probably do this. So here you can see an example in which I have, like another quantile plot with a negative bias. And this is a constant positive negative bias. Actually, this is wrong, it's not negative bias. Here, for example, calculating a mean error is relevant because the error is equal for the all distributions. Instead, if you look at the quantile plot on the right, you can see here the behavior is different. There is a discontinuity around 0. So this type of quantile plot tells me that for these distributions, it won't be very informative to calculate the additive bias. I would, the distribution exhibits two different behaviors, so I would need to split it in a sense. And actually, this type of behaviors essentially tells me that there is some misrepresentation in a process below freezing point. You see that the negative bias decrease essentially with the temperature. In the center, low center, you have scatter plots. And here you can see, for example, there is a growing of the error with the temperature. You can also see that there is a little outlier here. It's important to identify those because outliers affect some of the verification statistics. So a few examples here. Marginal distributions. Many statistics are used to compare marginal distributions. We have already seen some of the graphical tools to do it, like further than the quantile plots, there are histograms or box plots like this one in the image. From these box plots, you can immediately see that, well, the forecast has got like there is an under forecast essentially. To compare the marginal distributions, obviously, you can also compare the summary statistics that describe the forecast and observation marginal distributions. So there are different statistics, for example, that can describe the locations, like the mean or the median, or, for example, the spread of the distribution. So then you can have like the standard deviation or the interquartile range. The median and interquartile range are more robust and resistant than the mean and the standard deviations. So for example, if there is an outliers, median and interquartile range will be more suitable than the mean and the standard deviation. Continuous scores. So here I've listed some of the most common continuous scores, and I'm going to revisit them one by one, but just to give you an overview. The additive bias, which measures the attributes that is called the bias. Mean squared error or mean absolute error, they measure accuracy, or correlation coefficients, which is a measure of the linear association between forecasts and observations. Continuous scores are summary statistics, and they are used to evaluate forecasts of continuous variables, like, for example, temperatures. Summary statistics implies that they want to summarize in a single number the performance. So they're appealing for example, for administrative purposes, for example, in an operational environment when we want to monitor if the prediction improve with time. However, a single number, as Barbara was saying yesterday, cannot fully describe the complex relationship that exists between forecast and observations. So the recommendation is always to use a few of these statistics and to have them accompanied with some exploratory methods to make sure that you are aware if there is any problem in your distributions and that your distributions here is suitable. For example, if you have a bimodal distributions, it will be not informative to use the linear bias because you would compare the mean of something that is like essentially a point in the middle of the two modes of the distribution. So you need to have a look at your distribution overall. So continuous scores are suitable for continuous Gaussianly distributed variables, like, for example, temperatures here on the left, and they are not suitable for mixed or bimodal or right-skewed distributions. Here at the top, you see this is a distributions of a precipitation field. You can see there is a lot of zeros, no precipitation values, and then some precipitation values. And if you look at the axis, is in a logarithmic scale is very right-skewed. They're not suitable for binary or categorical variables, like clouds versus clear sky or sea ice versus water. They are not suitable for episodically spatially discontinuous on and off variables, like, for example, precipitation. So here at the bottom right, you can see a scatter plot. This is a precipitation field. And if you look at the maps of the precipitation field I used to produce these scatter plots, they resemble pretty much. But when you perform the scatter plot, you clearly cannot correlate these points, these bullet points. So here we go. Now I'm going to go through each one of these scores and talk a bit about their characteristics. So the additive or linear bias is the mean of the errors. So tell us, and is also equal to the differences between the mean of the forecast and the mean of the observations. In all my slides, the forecast is always Y and the observation is always X. The over bar always indicates averaging. So the mean error or the bias indicates the average direction of the errors. Positive indicates over forecast, negative indicates under forecast, and 0 is the best score. It does not indicate the magnitude of the error. In fact, because it has a sign, the mean error or bias is affected by compensating errors. So positive and negative error cancel out. So this is something that the bias is such a simple statistics to compute, but is so misleading because of this compensating errors. So this is an example that happened actually in real life. We had a new version of the model, which is plotted in red here. And when we looked at the summary scores, the bias was really worse. And everybody was like, why is worse? I know I improved the model. I don't understand. And then when we plotted the quantile plot, you can see that the red curve, the distribution is actually more near to the diagonal as it should be. But the old model had compensating errors. So you can see this is wind speed, and for lower wind speeds, we had some over forecast, and strong wind speeds, we had like an under forecast, and these errors in the blue curve compensates. So the resulting biases was smaller in magnitude. So this is an important thing to always to bear in mind with the bias. It can be misleading. One thing that we can do is to look at the mean absolute error. If the mean absolute error is much larger than the mean error, then the positive means that the positive and negative biases have canceled out. So we need then to look at other diagnostics like the quantile plot to find out what happened. The mean absolute error and the mean squared error. So the mean absolute error is the average of the magnitude of the errors, and it's a linear score. So each error has the same weight, is the absolute value. The mean squared error is the average of the squared errors, and it measures the magnitude of the errors weighted on the square of the errors. So because the mean squared error is defined by a quadratic rule, then it means that the large errors have more weight than the small errors. So this is good if you want to penalize the large errors. It might be interesting for winds, for example. We don't care about weak winds, but the one that, for example, damage houses or lead to, you know, it's like large impacts, we want to verify that the model got those right. However, this statistic, the mean squared error, is more sensitive to the large values and outliers. So it's sensitive to a large variance. For example, high resolution models are usually penalize more than their courses, for example, driving model counterparts, and encourage a conservative forecast, for example, with climatology. You can diagnose if there are, for example, outliers, looking at the value of the root mean squared error, which is the square root of the mean squared error. If this is much larger than the mean absolute error, indicates that there are probably some outliers in your distributions, and then you might want to plot your scatter plots to see it. So there is an example. So I have some temperatures here, and in the table you see the various summary statistics that I computed from these samples. So with no outliers is the first column. With an outliers equals to 30, this is the observed value. So you essentially I replace the value in blue with the value in red. And then I did another column where the value in red is not 30, but it's 50. I pushed it even further. So you can see how this affects the statistics. This is just one value on about 100 points. So you see the standard deviations, for example, is 25% larger than without the outliers. The root mean squared error is the one that is affected the most. You see like 3.59. And also the correlation is very affected. So correlation, mean squared error, and standard deviations are not resistant, so they are sensitive to large values and outliers, and not robust. So it's not suitable for right skewed or in general non-normally distributed values. Person or linear correlation coefficient. So this statistics measures an attribute that is called the linear association, and I'm going to explain exactly what it means. So it's what is it? So here you see is the mean of the. So these are the forecast and the observations products, but rescale. I take away the mean of the forecast and observations. So this is called the covariance, and is rescaled by the two standard deviations. So is the rescaled non-dimensional covariance, and the ranges between -1 and 1. 0 means that the forecast and observations are not correlated, and 1 is the best score. So the correlation is not sensitive to the bias. So if you look here, I've created an example to illustrate that. So this is, I'll start with the black points. These are, essentially they are, is an identical, the two distributions are identical, I just added a bit of noise, okay? And the correlation you see here was 0.98. When I add a bias, so I add a constant equals to 10 in this case, here, I obtain the blue sample. And the blue sample essentially has a bias, and you can see the correlation doesn't change at all. It's not sensitive to the variances. So if you look at the blue, the red dots, here I've shrunk the forecast. So I have I've divided by a factor of 2. And so the marginals of the forecast have got like a variance that is half than the original sample, and the correlation hasn't changed yet. So the correlation is not neither the inclination of the regression line, because which is the ratio of the standard deviations multiplied by the correlation. It measures simply the linear associations between the forecast and the observations. So you cannot see the biases with the correlations, nor a difference in the variances. What else can we say about the correlations? So the correlation is artificially inflated if I have a variable that has, for example, a climate trend. So here is another example. Concentrate on the black and gray curve here. This is actually a made-up example. These are not real data. Just to illustrate you this concept. So this, say, symbolizes a variable that has an annual cycle and is decreasing. For example, this could be the sea ice extent in the Arctic, okay? So you have that, increase and decrease with the season, and has an overall decreasing trend. So the differences between the gray and the black curve is just a little bit of noise. And when I calculate the correlation between these two variables, this is the perfect forecast, excluded a bit of noise, is 0.99. And these are the gray points in the scatter plots on the right. Then I took the anti-correlated signal, which is the red curve, okay? So here I have a lot of ice in the summer and not very much ice in the winter. So it's completely unphysical, this forecast. And these are the red points in the scatter plots. Because there is a trend, the trend essentially dominates the signal. So you see that even if it's anti-correlated, my correlation is still quite high, is 0.87, almost 88, okay? So this won't be a bad correlation, but is a completely unphysical forecast. If I take away the trend, then it will be anti-correlated. It will be minus 0.92. And then another example I wanted to add, say that your climate models guess the season correctly, but not the trend. Okay, so that's the blue line. Okay. Still, so in this case, essentially, I actually tilt the climate trend. Still, I have the same correlation as the initial curve. So I don't see neither the inclination of the trend. And this is because essentially it's like I am adding a bias and I'm changing the variances. So this is again what was shown in the previous slides. The correlation is not sensitive to the bias or to the variances, and is not the slope of the regression line. So this is just to show you that looking at correlation, it can be tricky, and we need to be aware of trends or also climatologies. So if you have a map, for example, that has got, say, some mountains on one side, you know, and plains on the others, well, the map correlation is artificially inflated by the presence of these two different climatologies. So you'll have, you know, a bunch of points on the scatter plots that are, for example, warm, and then a bunch that is cold, and artificially you'll have like a correlation that is positive just because you get the local climatologies. And you might have them wrong, but you know, you'll have a good correlation. So this is a very interesting article by Hamill and Uras that you probably are going to read in your life, that reveals how many, there are actually several statistics that are a victim of what is called the false skills or trivial skills, essentially, because they because the model is just capable of reproducing local climatologies. So what do we do in this case with correlations? We can consider the anomalies to essentially to evaluate forecast quality, not accounting for the fact that the forecast reproduce the local climatologies, for example, driven by topography. So in here, the y dash and the x dash are my climatologies, where essentially every point of a map is I subtract the climatology of that point, the long-term climatology. And this can be uncentered, like the one here at the top, or center, where I take away also the average of these anomalies. Good. Okay, so relationship between continuous statistics. Mean, squared error, bias, variances, and correlations are actually related. And this is a very important equation that you're going to find everywhere, and you need always to remember this relation. So here you have you can go through the algebra, actually, you can find it yourself. But this essentially means several things. So first of all, the mean squared error can be decomposed into, for example, two components: the square of the bias plus the variance of the error, which is the two standard deviations minus the covariance, twice the covariance. So this is actually exploited, for example, in operational environments. We use always the bias and the standard deviations to summarize more or less the performances. So this is an example where I plot the scores versus lead time. So each of these points is a score aggregated for this is over 3 months. It was July, August, September for each lead times of the forecast. And the continuous curves are the error standard deviations, and the dotted curves at the bottom are the biases. So here are these two terms in blue. And this is kind of, you know, when you have to look at several forecasts, is kind of, you know, is a good summary statistics. There is one small protagonist of these equations, the variance of the forecast, that plays an important role when we compare forecasts with different resolutions. When I have a forecast that has a higher resolutions than another one, has usually a larger variances. For example, this is actually is very true for precipitation, for example. So this leads to a larger mean squared error. So this is why smoother forecasts, for example, the ensemble mean, that you should never score, exhibit a smaller variance. And so they exhibit artificially a smaller mean squared error. So this is very important when you are going to compare forecasts that have got different variances and different resolutions. Bear this in mind. Sometimes you say, oh, my ensemble mean scores much better than my new high resolution models. Well, you need to look at other statistics. Eric is going to tell you more about that. The relationship between the continuous statistics can be exploited also to put them all, to display them all in a single summary diagram. This is an example of this type of diagrams. This is the Taylor diagram introduced by Taylor in 2001. So in this plot, you see here along the along the circle, you have the correlations. So for example, the K point here has a much larger correlation than the point I here. The distance from the number one, where is written observations, is the circles that you see here. These are the mean squared error. And here along the dashed line, this is the ratio of the two standard deviations. For example, the point D has got like a positive ratio. So it means that I think the forecast has a larger variance than the observations. Instead, for the point H is the reverse. So this is a good plot when you want to compare many different experiences, for example, of your forecast in a glimpse, and you want to see what's the difference between them. Skill scores. So skill scores, Barb went through this yesterday, compares the accuracy of a forecast versus the accuracy of a reference and offer a trivial forecast. For example, this could be the persistence forecast. This is, for example, suitable for sea ice forecast, or climatology. It could be also a long-term climatology or the sample climatology, or the random forecast. An example of this course is the reduction of variance. This is the skill score associated to the mean squared error, and the reference is the sample climatology, which means essentially that I forecast always what is the observed mean, the sample climatology. So let's see how this is, what is this essentially? So this is the mean squared error minus the mean squared error that is the reference, the mean squared error for the best forecast, minus again the reference. So the mean squared error for the best forecast is 0. So here I have 1 minus, here I have the mean squared error. So I have 1 minus because this one cancel out. And mean squared error, so this is the sample climatology minus the observations. That will be the forecast, the trivial forecast. So this is essentially the mean squared error over the observation variances. And this is in hydrology, so known also as a Nash-Sutcliffe efficiency. Okay. So the Nash-Sutcliffe efficiency was actually challenged by Gupta in a very nice article in 2009. And essentially Gupta was concerned about a few aspects of the reduction of variance, or NSE. So he essentially takes the composition of the mean squared error and plug it into that formula, and finds, shows essentially the NSE is equals to, well, can be decomposed into 3 different components. One that pertains to the correlation, one that pertains to the ratio of variances, but still the correlation is present in this component, and one that pertains to the bias. But here you have still the presence of the variance, of the observation variance. So what he was concerned about was that essentially, if you look at these three components in the NSC, the bias is still the bias term. It still depends on the variance of the observations. So if you have a forecast that has got a larger an observations where there is a larger variances, essentially the bias term gets less weight in the score. And another thing that they showed is that the term in red, essentially, is maximized for when the ratio of the variances is equal to R. And because R is the correlations, because the correlation is usually less or equal than 1, this means that it encourages smoother forecasts, because you see that when the correlation is less than 1, the forecasts have got less variance than the observations. So to address these 2 points, introduce a new score, the Kling-Gupta efficiency, which is instead is still divided into 3 distinct components. But in this score, there is no, for example, the correlation is not more into the ratio of the variances components, and the bias is also put in form of a ratio. So essentially, for all the scores for all the components, you'll reach the best scores when the components is 0. So essentially, when the ratio is, or the correlation is equals to 1, and this is actually the Euclidean distance from a perfect forecast at the point 1, 1, 1. So I think this is a score that is not used a lot in weather, but I think we should start looking at that. So continuous scores are sensitive to large values and can be not robust. So sometimes are evaluated by using the ranks of a variable rather than in actual value. And this is to eliminate essentially the outliers, because if I consider the ranks, what happens is that I transform the marginal distributions of my data into a uniform distributions. So what are the ranks? Here I have an example in which I have like my statistics. These are temperatures, and then I put them in order from the smallest to the largest. You see the second row, and then for each one of these points, I associate their rank, which I call I. So this is actually also equivalent to scoring probability space, right? Because if I look at the ranks, and this ranges between 1 and 8, but if I divide by 8, for example, here, I would range essentially almost from 0 to 1, like a continuous cumulative probability. So how do we calculate the cumulative probabilities from the ranks? Okay, I said we could use the rank over n, but in fact, actually, this is not a good way to do it, because in this case, I will have the first probability is above 0, and the last one is exactly 1. So I have an asymmetric definition of my cumulative probability. So this is not the best way to define a cumulative probability from the ranks. So then what I do, I take away 1. So the first one will be 0. My probability is 0 for the first rank, but then the last one will never reach 1. So this is not good neither. So let's see if I do I minus 1 over n minus 1. I always go through this resume to do it. So that's why I'm sharing it. So it's easy to remember. So I have, well, okay, for the first rank, I have 0, good. For the last rank, which is n, I have a probability of 1. This is good. However, you're not supposed to reach the 0 and the 1 probability. So this is okay, but still not optimal. If I do I over n plus 1, okay, this is symmetric because the first one is 1 over n plus 1, and the last one is n over n plus 1. And they don't reach the 0 and 1. So the one I prefer the most is the last one. But there are reasons to choose also this one. And maybe Ian is going to go through that, or probably Nachiketa later. So when we consider the ranks of scores or the probabilities, we can define different scores. For example, the linear error in probability space. So this is the mean absolute error evaluated by using the cumulative frequencies of the observations, and is defined here, where f of x is the cumulative probabilities of the sample x. So in this way, so you see that, for example, you translate, essentially, you transform your temperature into a cumulative probability. In this way, the tail of the distributions here, they're penalized less than the center of the distribution. So this is suitable when you have, like, for example, misbehaviors in the tails of your distribution. Another statistics that is computed with the ranks is the Spearman or the Kendall rank correlations. The Spearman rank correlation is the Pearson correlations between the ranks of the observations and the forecast, and essentially assess the relationship between two variables, assess if this relationship can be described using a monotonic function. So the relationship is no more linear, but it's just monotonic. Okay. This can be useful. Well, for verification, you want it to be linear, okay? But if in the future you want to assess, for example, the relationship between two variables, the Spearman correlation can be useful, okay? Because the relationship most probably is not linear if it's weather. So you might look at these statistics. And what I want really to say that the Spearman and Kendall correlations are more resistant and robust than the Pearson correlation. So here you have an example in which I have two examples actually. One is a monotonic functions. The Pearson correlation is 0.86 and the Spearman and Kendall correlation is standard 1. And then the second example in blue, where I have a little group of outliers, and you see the Pearson correlation is 0.81 and the other two instead are much higher, because they're less affected by this little cluster of misbehaving points. Something that I wanted to mention that it was not in the program, but I thought it's important to mention is circular statistics. So wind, for example, is a circular or a vectorial variables, and it can be verified using the fact that it's a vector. So usually, traditionally, how do we verify winds? So usually we score the X and Y components of the winds. So we look at, we decompose it as a vector. This is okay, but is we can do better. So we can decompose it into the wind speed and the wind directions. So have a, the magnitude of this vector and the direction. Here we can use, for example, for the wind speed is classic, the bias and the standard deviation of the error. For the wind directions, we can divide our plane into sectors, for example, of 30 degrees, and calculate multi-categorical scores that you're going to see with Mario. What I like to do is use the vectorial difference, or the vector root mean squared error, which is this green vector here. And this is actually is the modulo of so is the length of this vector, is the difference between these two, the observed and the forecast winds. I find it more informative, and also has a nice properties that with large winds, you have a large error. And for small, weak winds, you have smaller errors, which is usually for wind is what you want to have, because you don't care if there is like a very weak wind, if the direction is wrong. But if there is a strong wind, you want your forecast to get it. So here we go. I wanted to throw it there. Okay, so we are at the last part of my presentation. Aggregation. So aggregation is when we pull together all the values and for example, over a month, and we calculate our summary statistics. And it's important to aggregate because it leads to a more robust verification result. However, we cannot aggregate a sample if the sample is inhomogeneous. They has all to be homogeneous, otherwise we risk to cancel out errors. So we need to stratify our data set into homogeneous subsamples to make sure that essentially we extract the correct information. So this is an example in which I have a map, and say that I compute the bias over Fennoscandia. Well, all the negative bias on the mountain regions are going to cancel out with the positive biases on the other regions, and I'll have a perfect scores, but that won't inform me on how the forecast is really performing over Fennoscandia. So I would need to split this region. So looking at maps of scores is fundamental, because you'll have a lot of this type of behaviors in your data always. So look at the maps of scores. And this helps to define subdomains that are homogeneous. Another examples, usually when we scores, we look at the behavior of the scores with the lead time. So this is an example where I have a bias. And the bias a lot of times has got a diurnal cycle. So now suppose that you have forecasts that are initiated one at 0 Zulu and one at 12 Zulu. And you look at this forecast, but you put them all together with respect to lead times. What happens? That you have the night time forecast for the 0 Zulu run that are aggregated with the daytime scores for the 12 Zulu runs. So this diurnal cycles cancel out. So this is another way, on another occasion in which you need to separate the aggregation for the origin and the lead times, not only for the lead times. Otherwise, you'll cancel out the diurnal cycle. Aggregation. What is aggregations? So suppose you have now here, this is a monthly time series of daily correlation scores, and each of these points have been calculated over a region for a bunch of stations, okay? So now I want the monthly aggregated scores. So the monthly aggregated scores is not the average of these correlations, okay? People are sometimes tempted to say, okay, well, let's see how all these, correlation scores that are calculated for each day behave. So they look at the distributions, there you go, this is the mean. And sometimes they even say, oh, okay, there's a distribution that take away the tails, and this is the confidence interval. This is wrong. So the aggregation, as you know, it's like the correlation is not neither linear, so you cannot take the average of this to have the aggregation. Is the score that you obtain by pulling together all the data of all the stations of every day, okay? And you plot them all in a scatter plot, and then you calculate the correlation of that ball of points. So when you have a large amount of data, you might not be able to have all these forecast and observation pairs from all the stations into, you don't have enough space in the RAM, essentially, of your computer to put them all together. So the question is, how do you calculate the aggregated statistics starting from the daily aggregated statistics? So in the next slides, I want to walk you through this algorithm that you might want to code one day, step by step. There is a lot of math, and this is the last things I want to show you. And you have the slides, so you can go back to them if you need. So here we go. This is my example. I have n days. Each days I've got some stations, the report, and in an ideal world, all the stations will report daily, and you'll have the same number of stations every day. But this doesn't happen. So sometimes the station doesn't work because, I don't know, something happened to the stations, or the person that was in charge was sick that morning and couldn't report. So this sample size that you have every day is not constant. It's different, it's slightly different every day. So we start from the average, okay? So you have the average of the forecast, sorry, the average of the observations and the average of the forecast for every day, computed from all the stations that reported that day. So how do we calculate the aggregated averages to calculate the aggregated bias? So well, we start with 2 days, just to make it simple. So well, the average of day 1 and day 2, so together, would be given by essentially I sum all the values of day 1 and day 2 divided by the sum of the 2 sample sizes of day 1 and day 2. Then what I do, this is actually is algebra. You just essentially, you can split this. This is the average of day 1 with a weight, plus the average of day 2 with a weight. And these weights are proportional essentially to the sample size of that day divided by the aggregated sample size. So now I generalize for all the dates, okay? So here I have the aggregated average will be the weighted sum of all the averages by some weights, and these weights are the sample size of the day j divided the sample size of the aggregated samples, so which is all the sum of all the sample sizes of all the days, because when you look at the monthly aggregated values, you have all these values. Okay, so this is the aggregated. This gives me the aggregated average of the observations. You do the same things for the forecast, and then you can calculate the aggregated average. Number 2, aggregation of forecast and observation variances. So one important thing you need to know is that the variance of X, or of the observations, well, this is essentially the average of the squares minus the mean. If you develop this becomes essentially, this is the squares, and then you can take out the X squared. So this is the average of the squares minus, here I have twice the average minus the average, so it's minus the average squared. So these are the 2 very important components in which the variance decomposes. And it's from these 2 components that I calculate the aggregated average, okay? So the aggregated mean, this one, we have already evaluated it the slides before, is the weighted sum of all the daily means. The aggregated mean of the squares is identical. You calculate it with this, I call them actually the atomic statistics. You have the aggregated daily squares, weighted always by the sample size. And so you can obtain the aggregated variances by subtracting these 2 quantities. Forecast and observation, covariance and correlation. So the covariance, you can do the same math as you did for the variance. So here you have the product. You multiply these 2 equations and you obtain this. And then you try to take them out with respect to the averaging. And what you obtain is that you have the average of the products minus the products of the averages. So these are the 2 quantities you need to calculate to have the covariance. So how do you evaluate the aggregated average of the products? Well, similar to the average. So you have the products, the average of the products for every day, okay? And then you do the weighted sum. So the covariance is going to be equal to the average of the products minus the products of the averages, as here. And once you have the aggregated covariance, you can calculate the aggregated correlation, simply normalizing by the standard deviations. So mean squared error and absolute error. Well, the mean squared error, the aggregated mean squared error, you can evaluate it from the relations that I gave you in the very beginning. You have the mean squared error is equal to the squared of the bias minus plus the two variances minus twice the covariance. However, what I do in my code, I usually calculate it, okay? So I calculate the mean squared error daily, as well as the mean absolute error daily. And then I calculate the mean squared error aggregated as the weighted sum, like I did with the average. And this one, I have a double body check in my code. And I check that this aggregated mean squared error is identical to the one that I have with the formula. So this is the way you can calculate the aggregated statistics, the aggregated continuous scores from what I call the atomic statistics. So this is my assignment. So I have actually, I made up this should be, there should be an over bar here, okay? This is the orange lines are the averages. So I made up these numbers, and if you plot them, you see they have a sinusoidal behavior. I would like you to evaluate the aggregated annual bias, the mean square error, and the correlation from the given monthly statistics. I didn't give you the sample size because everybody knows how many days there are in each month. In alternative, if you think that 12 months is too much, you can do it on 3 months. For example, you can evaluate the aggregated summer or the winter correlations from the given monthly statistics. So to do that, you have to go through the maths that I just explained to you. You have all the formulas in the slides. So with this, I say thank you, and I'll stop for questions.
We're 5 minutes early. Good. We'll take the questions and discussion from the chat first, or
yeah,
will it open? Anybody can ask the question. First, we will have from the participants, then we'll go to the chat box.
Okay. So I can see J.U. Cheng. I don't understand why the root mean square error is not suitable for non-Gaussian distributed variable. Can we try root mean square error for a Boole distributed wind speed? Actually, we can, for sure. It's more affected by the fact that, for example, a right skewed distributions is affected. You'll have more weight on the values that are on the large values that are in the tail of the distribution, and you'll have less weight in the center. So it's that you can, it's not that you cannot compute it, for sure you can. You have just to be aware where it puts the weights. I hope it responds to your question.
Actually, Ayn had responded for that question.
Ah, good, excellent. So yeah, I agree with, yeah, I can see. I agree with Ian's comments, yes. There is a hand up. Akshay, I don't know how to pronounce your name, I apologize.
Kulkarni.
Go ahead.
Thank you. Nice talk by you actually, ma'am. It's very informative. But I have a couple of questions about correlations that you said, like a linear correlation coefficient that you said about earlier before Spearman and Kendall rank correlations. So I have a question about it. Like atmosphere is actually governed by non-linear partial differential equations. This question might be very basic and maybe you feel like, but like we have non-linear partial differential equations, which is already non-linear and dynamic. So why we are looking for the linear correlation from the linear correlation coefficient that we are calculating on daily basis? But our butterfly effect used to say in atmosphere there used to be daily changes. So why we are trying to check on daily basis like correlations with observations and forecast?
Okay, well, the forecasts and the observations are supposed to be identical, right? So that's why we look at the linear correlation, even if all our relationships are non-linear. I'm not sure if I understood completely your question, but this is what I would say. If I haven't understood your questions, though, maybe ask it again.
Sure. Like we have a atmosphere which is actually governed by nonlinear partial differential equations,
Yeah.
which itself says a nonlinearity in equations. So atmosphere is governed by nonlinear equations, and we are trying to correlate or associate our observation with some forecast, which is a linearly correlations. So is there any at such like dynamic correlations kind of stuff, or I wanted to explore in that. That's why I
Yeah.
got this question.
Yeah. So yeah, no, I think I understood the question. So
Thanks.
we are not at this stage, we are not assessing the real, the process, the dynamical processes. So we are not assessing the complex and nonlinear associations. We are just looking at the forecast versus observation, that they are supposed to be identical one to each other. But when, on the other hand, you look at the relationship between, say, variables, they are not linear, most of them. And so in that case, you can use other correlation like the rank correlations or the Sperman or the Kendall. But this is just, that would be just to look at relationship between variables, and then you can look if these relationships are similar in the observations and in the forecast.
Okay, thank you so much. Ma'am, I have one more question. May I proceed?
Yeah, I think so.
Okay.
Yeah.
You told about the like nonlinear correlation coefficient and Spearman and Kendall rank correlation. So how we can decide which one we can go with?
Well, you look at you do a bit of an exploratory analysis. So you look at your data first. So for example, you do a scatter plot, which works if you have, say, about 100 points, or 200 to 200s. If you have like 1,000 points, it's difficult with that. So you might need to, to find other way of exploring your distribution. But essentially, the idea is you look at your data and then you see if there is like a linear kind of associations, you can use the correlation. If it's not, if you see there is a parabolic relations, then you say, okay, this is not good. Or if there is a big outliers, you are aware that essentially your correlation might be affected by these points. So the idea is to do the exploratory analysis first.
I see. Thank you.
Oh,
Thank you
you're
so
welcome.
much.
Good. So I can take actually also questions if you have any other questions on my presentations. My email, both my emails are at the end of the presentation, so feel free to email me.
Sure.
Okay. Thank you very much.
Thank you very much.
Hi, Marion.
Hello.